Now that we've derived unit stream power and show how it relates to the slope and discharge of water in a channel, the next step is to relate it to bedrock erosion. So first, I'm just going to remind us all that this little omega, which is unit stream power, let me make these little annotations in gray just to keep it a little cleaner. Is equal to the fluid density, so it's 1,000 kilograms per meter cubed for water, times acceleration due to gravity, times the discharge in the flow divided by the width of the channel, times the slope of the flow. And we also know that we can partition that into two different major terms. So that part of this power is related to transfer of potential energy into kinetic energy per unit time. So PE to KE, that's option 1 per time. And then option 2 is B, which is potential energy to ME, so mechanical energy per time. And this mechanical energy term is this garbage can term that we kind of ignore when we're in introductory physics classes, but is actually quite important because this relates not only to the heat that is generated, which I mentioned earlier on, so we can think of things like shear heating. Because, just in the same way that when I'm going to do this in front of the mic, when you rub your hands together, you can feel that heat on the hands. And so that heat is related to the fact that the kinetic energy that you are expending, moving your hands back and forth with that 1/2 mass times velocity squared, is being converted into heat, and as kind of this kinetic energy to mechanical energy conversion. But then there's another kind of mechanical energy, and that is going to be actually breaking things. And what that means is that you can imagine that over time, with some mechanism or another, right? Remember, energy is just in terms of, as a conservative principle, it is process agnostic. So we could have a river channel bed that looks like this, and maybe there's some giant chunk of rock that goes flying down at the bed, and that creates a little microfracture right there. And those little fractures are what is necessary to eventually propagate and grow and create weaknesses that then allow material to be moved. And of course, it's also possible that your bed comes pre-made with fractures. It could have joints. It could have bedding planes. Those joints can be from cooling or from tectonics. The bedding planes could be from different layers of a sedimentary rock that were when it was first laid down. So in any case, there are these zones of weakness, and that is what allows the river to break up that rock, pick up pieces, and start carrying them downstream. And that brings us back to this kinetic energy term here. So if the flow is uniform, flow velocity is going to be constant, so we don't have anything related to speeding up or slowing down the flow. And then we also are going to have uniform sediment discharge, so that gets crossed off. So the only term here that's left for kinetic energy is erosion, because you're adding this extra piece of mass. So you can take this chunk right there. I'm going to do it in orange because that seems like an exciting color for breaking things. And that whole piece will go flying out into the flow. And it formerly had a velocity of 0, but now we've got our very own 1/2 mu sub rock squared term right there. And so that has transferred then this potential energy into some kinetic energy moving this rock. So what we want to know then is how this stream power might relate to a particular rate of bedrock erosion. And so I'm going to posit something. I'm just going to say, just as a first guess, that a erosion rate is going to be equal to some sort of K term. And I'm going to call this K sub E. Let's do that. And that is going to be the rock erodibility times omega. And maybe omega is raised to a power. I don't know. I'm just going to leave it linear at this point, just for the sake of having a first guess. And so this is something that we do as scientists. We say, well, I know that some fraction of this stream power is going to be converted into kinetic energy that's moving this rock downstream, number one. Number two, I know that we might have some constant that's relating these two terms. And in fact, I am going to rewrite this instead of having the normal E, just to make everything be a little bit more consistent, to have this little epsilon style E, just so we can relate those two together a little bit better in our minds just by seeing them. And so what you can imagine is that this rock erodibility term might be really high if these fractures can propagate and grow very quickly without too much extra mechanical energy being expended. On the other hand, it might be really small if this rock is really hard and competent and it takes a lot of mechanical energy to be expended to actually incise into that bed and create these fractures. This term might be really high if there are plenty of rocks in the flow that are capable of slamming into the bed and creating these fractures. It might again be quite low if there are no rocks in the flow, so just water moving over rock doesn't really cause erosion unless that rock can be dissolved. Or it might be really low if there's a ton of sediment, because then the bed is covered in a layer of alluvium that's blanketing it, and so there's no way to have rocks bash into the bed if it's completely covered. So thinking about that then, this rock erodibility term might be related somehow to sediment cover on the bed, and it might be related to the innate erodibility of the rock. So I'm going to write rock erodibility and sediment as tools for erosion and cover that protects the rock. And so then we have this rock erodibility term here, and then just the stream power right there. So there we are. It's just a nice, simple little linear equation. And this equation is going to be our starting point. So we're going to take this, I'm going to put a box around it, and next time we're going to consider how this equation could then lead to some convenient form that we can use to understand the rate of bedrock river incision and eventually overall landscape evolution.